Hello everyone, this is Shruti. Welcome to our channel Shiv Rising Star Academy. This is our 9th lecture on electromagnetic theory. In this lecture, we are studying about the Gauss's law and the application of Gauss law and some tricks of the Gauss's law for a competitive examinations. So, electric flux. Electric flux is the measure of electric field passing through a given area. Suppose we have an area, this is our area, we consider this is an area, and the electric field passing through this area, suppose this is ds, area ds, and the electric field E bar passing through this area ds is the electric flux. That is, we consider a small area, that is d phi is equal to E bar dot ds bar. And when we have to calculate the total flux, we can integrate this. So integration of d pi is equal to integration of E bar dot ds bar. So the integration of this d phi is pi, and the integration of this is the constant. Electric field is constant everywhere, so we can take it outside. So E bar integration of ds bar. So this is the area, or integration of the small area is the total area. So phi is equal to E bar dot, the integration of this is S bar. Here the dot product. And how we can open this dot product? Phi is equal to E bar, ES, this is not dot, ES cos theta. Using cos theta, we can open this dot product. So this is our flux. Okay, this is our equation number first. So in this way we can calculate the electric flux. Electric flux is nothing but measure of electric field. This is electric field passing through a given area. This is d phi is equal to E bar dot ds bar. This is our electric flux. Gauss law. Gauss law is the electric flux through a closed surface is 1 by epsilon naught times the charge enclosed by the surface. This is the Gauss's law. So electric flux phi through a closed surface, so close, is 1 by epsilon naught times the charge closed by the surface. So this is charge q. So phi closed is equal to q upon epsilon naught. This is the Gauss's law. Suppose this is our equation number 2. And there are some conditions for applying a Gauss law. So conditions, what are that conditions? The first condition is that the surface must be closed. This surface must be closed. Suppose we have a sphere. Okay. So we can apply a Gauss law on this sphere because this is the closed surface. Suppose this is a rigid body and this is closed. So we can apply the Gauss law on this rigid body because this is a closed surface. That is condition for the Gauss law, that is surface must be closed. Second condition is that the electric field is constant everywhere. So electric field is constant everywhere. Suppose we are applying the Gauss theorem on this pair. So in this, for that, the electric field is constant everywhere. That is, electric field must be constant at everywhere on the surface of this. If electric field is constant, then only you can apply the Gauss law here. Third condition is theta at every point is symmetrical. That is the third condition, that is theta angle is at every point is symmetrical. That is the theta, that is angle between the electric field and the area vector. Each and every point is similar or symmetric. Okay, when all these conditions are satisfied, then we can use the Gauss law. Okay, this conditions, the surface must be closed. Surface must be closed. And second condition is the electric field is constant at every point. Electric field must be constant, and the third condition is that theta is at every point is symmetrical. When theta, that is theta is the angle, that is angle between electric field, okay, electric field and the area vector A bar, which is normal to the surface. So theta, the angle between them, electric field and area vector, is a symmetrical everywhere. If all three conditions are satisfied, then only we can use the Gauss law there. Our equation number first is that phi is equal to closed integral E bar dot ds bar, and this is our equation number first. And what is our equation number second? Phi is equal to Q by epsilon naught. So combining these two equations, we will get Q by epsilon naught is equal to E bar dot ds bar. Okay, or we can arrange it like this: E bar dot ds bar is equal to Q by epsilon naught. In other words, Gauss theorem states that the surface integral of the electric field over a closed surface is 1 by epsilon naught times charge enclosed. So integral E bar dot ds bar is equal to Q by epsilon naught. This is the Gauss law. There are some tricks of finding the electric flux. So we know that phi total is equal to Es cos theta. Suppose consider a one surface, suppose this is surface, any surface, and the electric field, the direction of electric field E bar and the direction of the area vector S bar, both are in a same direction. So the angle, that is theta, between them is the 0 degree. So we put the cos 0 is 1. So this is Es, this is 1. So phi is equal to Es. So in this case, when the electric field and the area vector both are in a same direction and the angle between them is 0, so electric flux is the ES. So second is the when the, suppose consider this surface, and here the direction of the electric field, suppose this is the direction of electric field E bar, and the direction of the area vector S is the opposite, both are in opposite direction. So here theta is a 180 degree. So cos 180 is -1. So phi is equal to, this is E S and -1, that is minus. So when the direction of the electric field and the direction of the area vector in opposite direction, then electric flux phi is equal to minus ES. Suppose consider a surface, this is the surface, and the direction of this electric field and the direction of the normal, this is the direction of the normal, so S, this is E bar, so angle between them is 90 degree, theta is 90 degree, so cos 90 is 0. So when the angle between the electric field and the area vector is 90 degree, then electric flux is 0. So this is the some tricks of finding the electric flux. Simply we can remember, when the direction of the electric field and the area vector is in same direction, then electric field is positive, that is ES. When both are in opposite direction, the electric flux is the negative, sorry here flux, and the angle between them are 90 degree, then electric flux is 0. Question is that when a closed cylinder kept in a uniform electric field, then what is the electric flux? So this is the closed cylinder and we kept it in a uniform electric field. Then we have to calculate the electric flux. Suppose we consider this is the surface first, this surface is second, and this surface is third. So the electric field is uniform. So the direction of the electric field, so this is the direction of electric field E bar. So here the direction of the, consider the first surface, okay, for this is phi for first surface. This is the first surface and the direction of the electric field in a first surface, so this is the direction, and the area vector is always outward to the surface, so the direction of the area vector is always outward to this surface. So here the direction of the electric field, so this is E bar, and the direction of the area vector, this is S, suppose S bar or A bar, whatever we consider. So this both are in a opposite direction. So here theta is 180 degree, and we know that the cos 180 is minus 1. So phi is equal to E S cos theta. So here cos theta is cos 180. So cos 180 is minus, so minus ES. So phi 1 is equal to minus ES. This is -1. So electric flux to the first surface is minus ES, and the electric flux for the third surface, this is the direction of the electric field is E bar, and the direction of the area vector is always outward, so this is in this direction, outward to the surface, so this is S bar. So both are in same direction, that's why the angle between them is 0 degree, and cos 0 is 1. So phi 3 is equal to ES cos, this is 0, so ES cos 0 is 1, so this is ES, phi 3 is ES. So flux to the related to this third surface is ES, and when this is the direction of electric field and the direction of the area vector is outward, so the angle between them is the. When we consider this second surface, the direction of the electric field in this direction and the direction of the area vector is outward to the surface. So this is the direction of area vector, this is the direction of electric field, and the angle between them is 90 degree, and we know the cos 90 is 0. So phi is equal to 0. Phi 2 is equal to 0. So total flux to this cylinder is phi total is equal to phi 1 plus phi 2 plus phi 3. So phi 2 is 0. So phi 1 is minus es plus phi 2 is 0 and phi 3 is plus es. So phi total, this is minus, this is plus, so this is 0. So phi total is 0. So the total electric flux through this closed surface is 0. When a closed cylinder is kept in uniform electric field, then the total flux related to this closed cylinder is 0. That is, question is that find the flux through a curved surface. This is any surface, this is flat surface of this, and this is the curved surface of this. We consider the flux through a curved closed surface is 0. So total flux, that is 0. So we consider flux of closed surface is 0. So this is the closed surface, that's why we consider the total flux is 0, and the total flux is the addition of the flux of flat surface, that is phi flat, plus the addition of the curved surface, that is phi curve. So this is 0. So this is 0. So this is the flat surface. Okay. So on that surface, the direction of the electric field in this direction, so this is the direction of E bar, and the direction of area vector or normal to this, so this is the A bar. So both are in opposite direction, so the angle, that is theta, is 180 degree between them. So cos 180 degree is minus 1, so phi is equal to EA cos 180. So cos 180 is minus 1, so EA, or this is minus, so phi on flat surface is minus EA. So we can put this value here. So this is minus EA plus phi curve. So this is 0. So we take this right hand side, so phi curve is equal to EA. Okay. So this is the flux through a curved surface. One note is that the electric flux is independent of shape. Suppose this is the circular shape or spherical shape. The electric flux phi is Q by epsilon naught. Suppose this is the cylindrical shape, and the electric flux of this phi is equal to Q by epsilon naught. Consider the cubical shape. And the flux of this is Q by epsilon naught. So the flux is independent of shape. Some tricks of finding the electric flux. Remember this formula, phi is equal to Q1 by total into Q by epsilon naught. So here same is pair and one charge Q is given, and we have to find the flux phi. So here for the complete inclination of this charge q, we require another half sphere or semi-sphere, another semi-sphere. So for this is the charge, this is the one semi-sphere and this is another. For the complete inclination we require this two. Okay, for this two semi-sphere. So we have given one semi-sphere, that is given is 1, and how many amount of required for complete inclination of this charge? 2. That is 1 by 2 into q by epsilon. So 5. So in this case electric flux is equal to 1 by 2 q by epsilon naught. So it is given number of surfaces upon total how much surface required to complete the enclosed discharge into q by epsilon. So in this case phi is equal to 1 by 2 q by epsilon. For this complete sphere and the charge here, so we require phi is equal to q by epsilon naught. Here we have given semi sphere and the charge is here. So for the complete inclination of this charge, two surfaces one above the other is required. So the total surface required is 2. We have given 1, so phi is equal to q by epsilon. Similarly, for the another shape, like this is suppose this is cylinder and the half surface of this cylinder and this is the charge q. For this complete inclination of this charge, we require another similar surface. Okay, another similar surface, that is this surface we require. Okay, so we have given, that is given surfaces, one surface you have given, total these two surfaces require similar, that two surfaces required, and this is q by epsilon. So phi is equal to q by epsilon. Similarly, suppose we have an cube and the charge is q is here. So for complete inclination of this charge q, we require another similar cone. So like that, this is the our given cone, this is the charge. For this complete inclination of this charge, we require another cone. So we have given one surface, total required two surface into q by epsilon. This is the flux. Phi is equal to 1 by 2 of this 1 by 2 q by epsilon, and the flux of this phi is equal to, suppose we have given like this. So flux of that is q by epsilon, or we have given like this, flux of this is 1 by 2 q by epsilon naught. Okay, suppose this is one plate of the q. This is the charge q on here. Sorry, this is not charge here. Suppose we consider this is charge q on here. And for the complete inclination of this charge in a cube requires 6 surfaces. Suppose consider this is the sphere. Sorry, this is here. And then when charge q is here, so this is 1, 2, 3, 4, 5 and 6. 6 surfaces, total 6 surfaces are required for the complete inclinations of this charge q. So how many given? 1, required 6. So 1 by 6 q by epsilon, that is phi is equal to 1 by 6 into q by epsilon. This is the flux. suppose this is a cube and the flux of this cube is phi q by epsilon naught, and the flux of one surface of this cube, that is one face of the cube, that is 6 faces for this cube. So for given is one face and the total number of faces is 6 face into q by epsilon naught. That is the flux for one face of the cube is 1 by 6 q by epsilon, and the flux for this shaded region, so shaded region is the half of the face, one face, so that is phi for shaded is equal to half of the face. So face is the 1 by 6 into q by epsilon naught. So half shaded is equal to 1 by 12 q by epsilon naught. This is the flux of this shaded region. So this is the cube, and the cube has 8 curves. This is the 1, 2, 3, 4, 5, 6, 7, 8. And we have to calculate the flux of this curve, that is phi, that is given is the 1 curve, that is 1, and the total is the 8 curve, that is 1 by 8 into q by epsilon. That is the flux of the curve of the